talk about GPS. So before we get into GPS, let's talk about the big broad term Rnav, because you have probably seen Rnav on every single GPS approach plate. But what does Rnav mean? Rnav refers to area navigation. So if we take a step back and go through the evolution of air navigation, first we had NDBs, right? NDBs, all they did was point to the station, that's it. They were susceptible to wind homing and they didn't have radials. You couldn't really calculate wind drift whatsoever. So then they improved, and there came VORs. VORs now had radials. You could tell what side of the VOR you were on to from, and you could also correct for wind drift because you could see side-to-side movement on a radial. But the limitation with VORs was that there are only a few of them across the United States, and you only could travel on Victor Airways. So that was a little inconvenient. So then came Rnav. Rnav allowed you to go direct to points. So instead of taking Victor Airways between VORs, you can go here, direct here, direct here, direct here, and the Rnav system would be able to do that. How it did it, old Rnav had a few tricks up its sleeve. One type of Rnav is called VOR DME Rnav. So it tells you how the Rnav works. Use VORs and DMEs, but you don't have to physically tune them. The Rnav system has a database with all the local VORs and DMEs around the area. What it's going to do is going to auto-tune these VOR and DME stations and triangulate your position using local VOR DME stations. So this radial, this distance, it knows you're right here. That's one version. Another version, it's called DME Rnav, and we can find that actually in the AIM. Where's my AIM? There we go. So AIM 1-2-1. Here we go. Here we see different types of Rnav. We have DME Rnav. It works almost the same way. It just takes distances from different DME stations, triangulates your position that way, instead of using VOR and DME. The last one is called inertial navigation. So inertial navigation, it senses movement. I kind of call this a blind kid in a box. So to picture this, put yourself on a moving office chair and then blindfold yourself. Initially, you will know where you're at, right? If someone comes and pushes you around with a blindfold on and you're on that wiggly chair, you'll probably know where you're at in the room. But if you get pushed around for the next 20 minutes, you're probably going to get lost because you're going to forget where you are. That's the same thing how inertial navigation works. You tell the system you tell the system where you're at right now. The system then senses all the movement you make and then guesses your position off of this movement it senses. It does this through different types of gyros, electronic or physical gyros. Pretty advanced, but it's kind of cool. So what this meant was that they used DME Rnav, VOR DME Rnav over the land of the United States. But then once you go on longer flights, for example, Trans-Pacific, Transatlantic, where there's no VOR or DME stations, you must use inertial navigation to get direct somewhere because there's no radials over there. So this came with a limitation. Because this drifted over time, right, it forgets where you are over elongated periods of time, things can get a little off. So an example of this, actually, an incident happened. Korean Air Flight 007. So Korean Air Flight 007 took off out of Anchorage, Alaska. If I can pull it up. There we go. So took off out of Alaska, and it was supposed to go to Seoul, South Korea. But instead, it was using INS, so it drifted and it flew directly over Soviet secret military base. So what the Soviets do, they shot it down. So everyone died. So then the United States government was like, hey, we got something called GPS. I think it's kind of useful for you. And so that's how GPS came to be. And so that's why there's a difference between Rnav and GPS. Rnav, less capable, old version. GPS, the new version, really nice. So GPS is more capable than normal Rnav, but in terms of what their uses are, they can both go direct to points. Their uses are the same. All right, so let's get into GPS. So GPS, it triangulates your position using satellites instead of UR and Ii.A. So if we have 3 satellites, 1, 2, 3. Boom, boom, boom. It triangulates your position into a 2-dimensional plane. So you know your 2D location. If we add one more, now you can triangulate your position in a 3D plane, 3D position. But in aviation, we want to be a little more precise, so we have 5 satellites. So with now 5 satellites, we have this thing called RAIM, and we can read all about it in AIM 1-1-7. All RAIM is it's an onboard monitoring system. RAIM stands for Receiver Autonomous Integrity Monitoring. What that means right there, see, RAIM. What that means is it's just monitoring the data received by these satellites and determining if it's reliable or not reliable. So now if we add in one more satellite, there we go. If we add one more satellite in the mix, now we have a thing called FDE, fault detection and exclusion. So if RAIM detects that one of these satellites is dead or faulty, it's going to chop it off. You're gone. And then it's going to replace that dead satellite with this new satellite. And you still have RAIM. And you still have reliable GPS. If you were to lose RAIM at any point in the flight, you no longer have GPS capabilities because your GPS is considered unreliable. Cool. If you read a little bit more, it mentions something about baro aiding. What baro aiding means is your GPS receiver in your aircraft is taking data from an altimeter or has its own altimeter to get vertical navigation. So in that case, to get RAIM, you only need 4 instead of 5, and to get FDE, you need 5 instead of 6 satellites. So it just chops everything down by 1. All right, so that brings us into WAAS. What is WAAS? WAAS, we can read all about that in AIM 1-1-18. Anyways, WAAS stands for Wide Area Augmentation System. What WAAS does, it makes GPS much more accurate. So you can think of GPS as being accurate within like 50 feet. WAAS now brings it down to 5 feet. So it can precisely pinpoint you in a single room now. Anyways, how WAAS works. Here's a normal GPS satellite, like what we were talking about up here. It takes data from this satellite, and instead of going to your plane right away, it's going to send it to the ground. And we can kind of see the names of all the different stations right here. Right, the first station is called a reference station on the ground. Reference station's job is to receive information and send that information to a master station. The master station does all the correction for timing errors and then sends the corrected signal to, oh, there's a picture right there. Then sends the corrected data to an uplink station. From the uplink station, it goes to a geostationary satellite, and from there it goes to your plane. So what it looks like is this. Normal satellite to a reference station, master station where it does all the correction, master station, uplink station sends it to a geostationary satellite. This just means that this rotates with the Earth. So let's say a geostationary satellite was right above Arizona at all times. It's going to stay over Arizona 24/7. From there, then it goes to your plane as a corrected signal. And so it does this one by one with each one of your satellites. And you can kind of see this on your GPS status page. You'll notice a small little D comes up underneath every satellite status once each satellite gets corrected. So that's what it means. All right. So with WAS now, you have additional capabilities. Because your GPS becomes more sensitive, now we can shoot more sensitive approaches. So here are all your choices. You have Lnav, you have Lnav/Vnav, you have LP, LPV, LP plus V, Lnav plus V. All right, so a quick way to remember this. I'll put a star right here actually. We'll talk about this in a sec. But the only one that does not require WAS is Lnav, so no WAS. Everything else requires WAS essentially. So that's an easy way to remember that. So with WAS, if you remember this GPS scaling, go from 2 to 1 to 0.3, right? LP acts like a localizer. What that means is the closer you get to the runway, the more sensitive the GPS gets. So, assuming the runway is right there on the tip of the V, the closer you get to it, the more sensitive it gets. It scales down just like a localizer does, but it does not use a localizer. LPV is just that. It requires WAS, gets more sensitive, but it has vertical guidance, approved vertical guidance. So you have a DA with LPV. That also scales down. Anything with a plus V, all that means is that it's an advisory vertical guidance. It does not give you a DA, it's just your GPS trying to help you out and gives you a generated glide slope. But the FAA doesn't know about it, so it still remains an MDA. So this one has a DA. So Lnav Vnav, this one's a little weird. Lnav Vnav, actually, we'll talk about Lnav first. Lnav does not scale down, right? It stays 0.3 all the way down. Lnav Vnav is just that. However, it has approved vertical guidance, but it's not as sensitive as LPV. So we think about the days back when Rnav was a thing, right? And not GPS. You could have a baro-aided Rnav system where it takes data from an altimeter source. So that's what was providing you vertical guidance. So that can bring you down to a DA. So really, Lnav Vnav is WAS or a baro-aided Rnav system, one or the other. So if you go to the Rnav GPS 2.3 in a Coolidge, right, you'll see both LPV minimums, Lnav Vnav minimums, and then Lnav minimums. Assuming you have a system that has WAS, baro-aiding GPS, and Lnav, if you lose WAS, you go from LPV down to Lnav Vnav because you have baro-aiding. And then if you lose baro-aiding, then you'll go down to Lnav. But because we don't have a baro-aided GPS in all of our planes, you would go from LPV straight down to Lnav.